Good morning, students, or for some of you, good afternoon. I know that you are probably just crawling out of bed. I have 2:21 in the afternoon. It is Thursday, April 2nd, 2020. And the point here is that I'm going to do a instructional video just for you because you're special. I'm hopeful that this is helpful for you. If it is, you know what, I'd like you to tell me. And if it's not, I'd like you to tell me what I could do to make it more helpful to you. So keep that in mind. The objective here, kind of a two-part objective. First of all, I want to review with you the major topics and major ideas that we have been using in our study. And also I want to just work some problems for you, demonstrate some problems for you, the kind of problems that you've seen on your practice sheets, mini quizzes, and that you're going to see on your upcoming quiz. So let's get started. First of all, let's start with the review of the law of sines. So recall that the law of sines allows you to find side lengths and angle measures for any kind of an angle, or any type of a triangle is what I meant to say. And we know that if you have a triangle that, let's say, looks like this, and you know this side, and you know this angle, and you know this angle, but you do not know this side. The law of sines simply says that the ratio between the sine of an angle and the side that's opposite that angle is the same as the ratio between the sine of any other angle and the side that's opposite that angle. So using the law of sines simply involves setting up a proportion, cross-multiplying for whatever unknown you're looking for. So I would say here that the sine of 35 degrees is to the side that's opposite that angle, 12, as the sine of 50 degrees is to the side opposite that angle, which is the value we're looking for, x. X then would equal 12 times the sine of 50 divided by the sine of 35. I'm going to let you figure out what the final value is here, but at this point you would go to your calculator. You would make certain that you are in degree mode. We're going to be in degree mode for all these problems. Radians aren't going to be involved with these types of problems. And just round your answer to the nearest hundredth. So this is our extended proportion. This is how the law of sines is usually presented. We say the sine of an angle and the side opposite that angle. So angle alpha corresponds to the opposite side A. The sine of beta, its opposite side is designated B. And the sine of gamma, its opposite side is designated C. So just in the event that you are unfamiliar with these variables, remember, this is alpha, this is beta, and this is gamma. And I can tell you I've seen just about every representation for that variable right there. People kind of make their own shapes for gamma. So don't worry about it. Once again, just to emphasize, this side is opposite that angle. So law of sines says that each one of these is equal. In other words, the sine of an angle divided by the length of the side opposite that angle is a constant for all three angles and all three sides in a triangle. So that's the law of sines. And if you know two sides and one angle, you would then use the law of sines to find the angle that you don't know. And that would involve your final step in that would be using the inverse sign, because you folks know that whenever you are trying to find the angle, you use the inverse. So what's the whole deal then with needing to have a second law, the law of cosines? Well, look at this proportion for a second. Okay. In all these problems, you're given some information about the triangle, usually 3 pieces of information. And then the directive might be for you to solve the triangle, which just simply means you're being asked to find all the values, side lengths, angle measures that you're not given at the outset of the problem. But let's suppose that the given information is the following. Let's suppose you are told the degree measure of alpha, and you are told the length of side B, and you are also given the length of side C. So you have 1, 2, 3 pieces of information. The problem is that if you plug that in where I've circled those values, you do not have the information that you would then need to set up a proportion and cross multiply. So what do? Well, what you do is you go to using the law of cosines. Now, the law of cosines is kind of ugly to look at at first, and it's a little scary because perhaps you get a little confused which angle's alpha and which angle's beta and that kind of thing. And it doesn't really matter. I'm just going to write one representation here for the law of cosines. A squared equals b squared plus c squared minus 2 times b times c times the cosine of, and this is the important point, times the cosine of the angle that would be across from that side that I'm gesturing to, angle alpha. So this side right here in your expression is always the side that's opposite that angle. Let's do a problem. Here's my triangle. I'm trying to find the distance from this point to this point. That's what I'm trying to do. And I don't know, let me make up a scenario. Maybe that I'm trying to find the distance from those one point to the other, but there's a lake here. So this is a lake, or say a pond or something of that nature. So it makes it difficult to measure how far it is from this point to this point. So here's what you do. Pick another point, say this point right here, and you measure this distance over to this point. I don't know, maybe that's, 200 feet. And you measure the distance to this point here. Okay, let's say that's, 310 feet. Now, you have some implement that allows you to measure this angle right here. And there are such implements. You could, if you use your imagination, you could you could imagine making such an instrument, and all you would need is a protractor. You guys know what a protractor is. And a protractor goes from 0 to 180. And then you need some sort of an instrument that you can sight through, some sort of tube, let's say. And as you look through the tube, you could pivot that tube and move it along your protractor, and you could figure out how many degrees that would be. So let's suppose you're standing right here and you're looking at that point, and you've got your protractor here. You've got the implement that you've devised using this protractor. And you're able to determine that this angle right here is 80 degrees. So you would now use the law of cosines to find the distance from this point to this point. And you would simply say that x squared is equal to this side squared plus this side squared minus 2 times 200 times 310 times the cosine of the angle that's opposite that side, which would be the 80-degree angle. This angle is opposite that side. Now, what you would do then is, algebraically, is take the square root of both sides. So x equals the square root of this expression. It's time to go to the calculator, but let me caution you about something. And this is a common mistake. When you enter this under this long radical sign in your calculator, depending on what version of the TI that you have, sometimes when you put this in, a parenthesis opens up right here on your calculator screen. When you hit cosine, a parenthesis opens up right here. So oftentimes, depending again on the version of the TI that you're working with, your last two keystrokes before you hit enter are going to be close parenthesis, close parenthesis. So don't forget to do that. So remember, your calculator always follows order of operation. So you have to use the parentheses strategically. When you're doing this, or you won't get the right answer. So just be careful with that. And again, I'm not going to do the calculator part here. I don't want to take time to hit all those buttons. All right. So this is an example over here of using the law of sines to find one of the side lengths. This is an example of using the law of cosines to find one of the side lengths. Let's do a problem where we're going to use the law of cosines to find the degree measure of an angle. So here's a triangle. And I'm just making this up as I go. So let's say this side over here is 36 units. And this side over here is 15 units. And this side is, say, 27 units. So I know the three sides. And I'm going to put theta right here. And our job is to figure out the degree measure of theta. Well, if you take this expression right here and you manipulate it algebraically to solve for the cosine of the angle, what you would get is that the cosine of alpha is equal to b squared, that's that b squared, plus c squared minus a squared, all divided by 2 times b times c. I think this would be a good time to make this point because I just made it so recently. When you take this expression right here, and you enter this into, you have your numbers, you have your values for A, B, and C, and you enter this into your calculator. always encompass the numerator in parentheses and the denominator in parentheses. So just like up here when we were doing this calculation for finding the side length by using the law of cosines, we had this big radical here. Our last two keystrokes were close parenthesis, close parenthesis. Very likely the same thing is going to occur here. So let's plug in. And by the way, alpha then is going to equal the inverse cosine of this entire expression. B squared plus C squared minus A squared all over 2 times B times C. So if I take these numbers and I plug them in to this expression, I'm going to have that theta, instead of alpha, is equal to 15 squared plus 27 squared minus 36. Remember, 36 is opposite theta, 36 squared, all over 2 times 15 times 27. I just want to say again, I know you don't even want to hear me say it. When you put this guy into your calculator, put the top in parentheses and put the bottom in parentheses. Make sure you do that. Oh, you know what I forgot? I'm sorry. Right here, you're going to have to hit second cosine on your calculator. So theta is the inverse cosine of this expression. And you could run that on your calculator and get the answer. So this involves a quick review, maybe longer than I wanted to take and you wanted to listen for, of the law of sines and the law of cosines. When do you use the law of cosines? When you can't use the law of sines. Law of sines is always a little quicker and more efficient. If you're solving the triangle and you're supposed to find all the parts that you don't know, if you use the law of cosines to find the first part, then resort back to using the law of sines to find your other unknowns. All right, let's go on. We're going to do some problems involving the area of a triangle. Okay. And you probably didn't realize it, but there's more than one way to find the area of a triangle. Here's your basic formula here. Area of a triangle is 1/2 times the base times the height. And you guys have known this forever and ever and ever. I'm gonna redo this on another sheet of paper. Hold on, apologize. Area of a triangle. 1/2 times base times height. So if you have just an average run-of-the-mill everyday triangle sitting around, this would be your base. The height, however, is always the perpendicular distance or the length of the altitude drawn to the base. So you'd take this value, put it in for B, take this value, put it in for H, and do your arithmetic, and you're home. So what's the big deal then? The big deal is this. For a lot of problems, you're not going to know B, and you're not going to know H. So you're going to have to use some trigonometry trick most of the time to figure out one of those two values before you could actually compute the area. So let's suppose we have a right triangle. Okay. So here's a right triangle. And I tell you that the hypotenuse is 5, and I tell you that this leg is 3. And then I ask you to find the area. The 5 has nothing to do with finding the area. The 5 does have something to do with finding this side here, the other leg. And everybody who's watching right now knows that that would be 4. So for a right triangle, the area is going to be 1/2 times the leg times the other leg, because the two legs are the base and the height. So for this situation, we'd have area equals 1/2 times 4 times 3, which would be 6. And that's going to be our area, 6 units. So the moral of this story is that sometimes you'll have to apply the Pythagorean theorem to find one of your legs so that you have the two values you need to plug into the formula. Let's look at this situation here. Make up another problem. Once again, we have a right triangle, but I'm going to tell you that this is 30 degrees, and I'm going to tell you that the length of the hypotenuse here is, say, 40. And that's all I'm going to tell you. And I'm going to ask you, what's the area? Well, what you're going to do now is you're going to apply what you know about a 30, 60, 90. And what you should know about a 30, 60, 90 is that whatever the hypotenuse is, the leg is half, the short leg is half, and the long leg would be the short leg times the square root of 3. Now this becomes your height, and this becomes your base. So your area then would be 1/2, just using this standard formula up here. Area is going to be 1/2 times your base, which would be 20 square roots of 3, times your height, which is 20. If you were going to express this in simplified radical form as an exact value, you'd have 50 square roots of 3. And if you needed to get a decimal approximation for this, you just go to your calculator. Look at this situation. Here's a triangle. And let's suppose I tell you that this is 40 degrees. And the length of this base here is 30. And then I tell you that this side right here is, let's say, I don't know, 22. So this is the base here. This is your formula. Area equals 1/2 times base times height. So you got a value to put in for B. You can do that right now. 1/2 times 30. But what you do not have is a value to put in for H. So I'm going to drop an altitude down. Altitude always perpendicular to the base. And we're going to focus on this right triangle right here. And I'm going to set up a little sine relationship to solve for H. So when I'm looking at this right triangle right here, I'm going to say the sine of 40 degrees is equal to opposite over hypotenuse, H over 22. If I multiply both sides of this equation by 22, I'm going to have 22 times the sine of 40 degrees is equal to H. So then I would take this value and put it in for H. So to get my answer then, I'm going to have 1/2 times the base, which is 30, times the height, which is 22, times the sine of 40 degrees. This is what I would go to now in my calculator and get my final answer. So I want to take this problem right here and just kind of generalize it. Here's what we did. We knew this side. Let's say this is side A. And we also knew this side. This is side B. And we also knew this angle right here. I'll call it angle C. And if you look at what we ended up with, right before we took this and put it in our calculator, what we had was that the area is equal to 1/2 times A times B times the sine of C. This becomes another formula, if you will, for finding the area of a triangle. Let me describe the formula to you. You got two sides, A and B, and you've got an angle that's formed by those two sides. So what I'm telling you is, anytime you know two sides and you know the degree measure of the angle that's formed by those two sides, you can just use this formula. This is probably the one that you're least familiar with, but it's the one you're probably going to use the most from this point going forward. So let's make up another problem here. Let's suppose you have this triangle. And you know this angle right here is 93 degrees. And this side here is 14. And this side over here is 23. And you want to find the area. You're just going to take 14 and 23, put them in for A and B, take 93 degrees and put it in for C. So your area then for this triangle is going to be 1/2 times 14 times 23 times the sine of the angle formed by those two sides, which is 93 degrees. Take this and go to your calculator and get your answer. Let's do some more problems. Sometimes you'll have a triangle that doesn't give you enough information to just plug into this formula. In other words, you may not know A, B, and C. So what does that mean? That means you may have to use the law of sines to find B or to find an A value before you can plug in here. So, you'll have several steps involved with finding the area. Let's do one of those. So here's a triangle here. And I'm going to tell you that this is 40 degrees. And this is 60 degrees. And this side over here is, say, 32. And this side here, we don't know. We don't know. But we want to be able to find the area. So let's think about this. If I wanted to find this angle right here that I'm put a little dot in, that's a quick and easy thing to do because the three angles all have to add to 180. So these two guys are 100. So this guy would have to be 80. So once again, 80 was not given. We use the fact that the three angles in a triangle have to add to 180 to get the 80. And we want to use this formula. We want to say the area is 1/2 A, B, sine of angle C. All right. So I could say that this would be C. This would be angle C. And I have one side, let's say A, but I don't have B. So what I'm going to do then is I'm going to set up a little law of sines proportion to solve for this side right here. I'm going to call it X. And so I would say the sine of 40 degrees is to 32, as the sine of 60 degrees is to X. X then would equal 32 times the sine of 60 degrees divided by the sine of 40 degrees. Now I'm going to get my calculator. And I'm going to find this value right here. So I'd have 32 sine of 60 divided by the sine of 40. And I'm coming up with 43.11. So I'm going to write that up here, 43.11. Now, I'm going to use 32, 43.11 for A and B, and my angle C is going to be 80 degrees. So the area then is going to equal 1/2 times 43.11 times 32 times the sine of the angle formed by those two sides, which is that 80-degree angle. And then you go to the calculator to get your answer. So just to recap this problem, we didn't quite have enough information at the outset in order to plug into our formula, this formula here. But we use law of sines to find a side, and then we had enough info to plug into here. I hope you're all able to follow that. Let's do some more problems. Look at this one. Now, on this problem, you have a couple options. First of all, as soon as you see that you don't have, that you're given the lengths of 3 sides, you're probably going to be thinking that you want to use Heron's formula or Heron's law. Remember, Heron's formula looks like this. It says that the area of the triangle is equal to the square root of S times S minus A times S minus B times S minus C, and you got to take the square root of that whole expression. S, by the way, is the semi-perimeter. So let's go ahead and do this very quickly using the Heron's formula. The semi-perimeter here is half the perimeter. So I'd have 13 plus 13 plus 13 divided by 2. So I'd have 39 divided by 2. That'd be 19.5. The area then is going to be the square root of 19.5 times 19.5 minus 13 times 19.5 minus 13 times 19.5 minus 13. At that point, you go to your calculator and get your answer. But here's the deal. You guys know that if all of these sides are the same, then all of these angles have to be the same. And since you actually do know the angles here, we could go back to the formula that the area is 1/2 AB times the sine of side C. So I would have 1/2 times 13 times 13 times the sine of 60 degrees. Now go to your calculator. And I'd be willing to bet that when you put this in your calculator, you get the exact same answer as when you put this in your calculator. But let's suppose that we have a triangle in which the sides are all different lengths. This looks like it's about 12 units long to me, and this looks like it's about 29 units long. And let's suppose this is 30, let's see, 29 and 11 is 40. Let's go 35. There we go. And we want to find the area. This is definitely a Heron's law problem. So I'm going to, first of all, I'm going to find my semi-perimeter. So I'd say 12 plus 35 plus 29 divided by 2. So this would be 64, and 12 would be like 76 divided by 2, and that would be 38. Let me check that. 30, 50, 14, 64, and 12 is 76 divided by 2 would be 38. So the area then would be the square root of 38 times 38 minus 29 times 38 minus 12 times 38 minus 35, and just plug it into your calculator. You could put it in just like you see it here. Use parentheses, then hit enter at the end. You'll be good to go to get the area. So just to recap these problems here. This is really an equilateral triangle. So you kind of automatically know all the angles are 60. I would use this method. I think it's quicker. If you want to use Heron's law, you're fine. It won't take that much longer. In this triangle, however, we have 3 sides. We have no angles. And someone usually is thinking, well, gee, can't you use law of cosines to find one of those angles? And the answer is absolutely. So if you wanted to use law of cosines to say, find this angle right here, you could do that. And then once you have that angle, you could go back to using this formula here. But I think it's going to be a lot longer. I think that's going to take you longer to use law of cosines and then come back and plug into here than it would be to do Heron's law on this one. Heron's law seems like it's a cool thing, but if these numbers that represent the lengths of the sides are unfriendly numbers, let's say they're real long decimals or they're some sort of weird fractions or something, then using Heron's law becomes rather cumbersome just to enter that stuff into all those ugly numbers into your calculator. All right, look, I'm going to give you, I'm going to do some random problems now. Do some random problems, and I guess they probably are random, even though there's a real good chance that I have a specific purpose for showing them to you. This is a parallelogram. And I'm going to tell you that this angle right here is, I don't know, let's say 50 degrees. And I'm going to tell you that one side of this thing is 80, and the other side has a length of, let's say, 60. And I'm going to ask you to find the area, okay? I ask you to find the area of this parallelogram. Here's the first thing you got to remember. The area of a parallelogram is base times height. The area of a parallelogram is base times height. I probably should be telling you that the area of a parallelogram is not 1/2 base times height. And the reason I say that is because if I give this problem, find the area of the parallelogram, and somebody gets it wrong, it's almost always because they tried to take half because they're just so used to using the formula for the area of a triangle. So the base is 80. So we're good to go on the base, but we don't have the height. The height is always going to be the perpendicular distance or the altitude between the 2 parallel sides. So I'm going to call this H. And I'm looking at this right triangle right here. And I'm going to use a little sine relationship. And I'm going to say the sine of 50 degrees is opposite H over hypotenuse, which is 60. Or I'm going to have 60 times the sine of 50 degrees is equal to H. Now I have all the values I need to plug into my formula, base times height. Base is 80. Height is 60 times the sine of 50. Then you're going to go to your calculator and get your answer. Go to the calculator and get your answer. By the way, while I have this drawn here, let's suppose I draw in the diagonal here. And I ask you to find the length of that diagonal. I'll just call it D. This 80 here transfers to here. And you can see that if you focus on this triangle, this half of the parallelogram, you're going to be able to use law of cosines to find d. And I would simply say d squared equals 60 squared plus 80 squared minus 2 times 60 times 80 times the cosine of that angle, 50 degrees. Then you'd have to take the square root of that whole expression to actually find d. Be careful with your how you enter that in your calculator. Let's do another random problem here. Here's a circle. Here's an angle, a central angle of the circle. I'm going to tell you that this angle is 70 degrees. I'm going to connect the endpoints of the two radii with a line segment. By the way, that line segment that connects those two endpoints is called a chord. That's a term from your geometry class. And I'm going to tell you that the radius of this circle is 50 inches. And what I'm going to ask you to do is figure out the length of that chord. Let's just call it D. I want to figure out the length of that chord. Okay, so students, this is really just nothing more than a law of sines problem. Why is it a law of sines problem? It doesn't seem like we have enough info to do the law of sines. Well, we actually do, because in a circle, all the radii are the same. So if this is 50, this is 50. Here. And it seems like we just have this one angle here. We could use law of cosines right now. And we could say, if we wanted to, we could say that d squared is equal to 50 squared plus 50 squared minus 2 times 50 times 50 times the cosine of 70 degrees. And then d actually equals the square root of that whole expression. But look, any triangle that you draw inside a circle like this is going to be an isosceles triangle. So not only are these two sides the same, but these two angles have to be the same. In an isosceles triangle, the base angles are always congruent. So if this guy is 70, these two angles got to add to 110, which makes each one of them 55 degrees. So the point that I'm making to you right now that I'd like to have you remember is that this triangle that you draw inside a circle in this way is going to be isosceles. And not only are the sides, these two sides going to be the same, but these two angles would have to be the same. So now you can just set up a law of sines, and you could say the sine of 70 degrees is to D, the side opposite, as the sine of 55 degrees is to 50 inches. And cross multiply, D is going to equal 50 times the sine of 70 degrees divided by the sine of 50 degrees. So whether you use law of cosines or whether you use law of sine, you should come up with the same answer for both of those. I want to say one more time. In this situation, this triangle right here, this triangle is going to be isosceles. Important to remember that. Important to remember that. All right. Let's do a couple more random problems. If you've already fallen back asleep, I apologize. Let's do a problem involving baseball. Let's do a problem involving baseball. So we're considering a baseball field. We're considering a baseball field. And let me try to draw a baseball field here for you. So this is a baseball field, and we're gonna make this home plate right here. This is home plate, and we're gonna put the pitcher's mound right about here. That's the pitcher's mound, and this would be first base here. And this would be second base. This would be third base over here. Now, students, I know we call it a baseball diamond, but in actuality, it's just a square. It's just a square. All the sides are the same. And in fact, the base path is 90 feet. Base path is 90 feet all the way around. And the distance from the pitcher's mound to home plate is 60.5 feet. So the question I'm going to ask you is, how far is it from the pitcher's mound to first base? We'll call that X. So here's what we have right now. We have this length from pitcher's mound to home plate is 60.5 feet. The base path, home plate to first base, is 90 feet, and I'm asking you to find the distance from the pitcher's mound to first base. Guess what? You don't have enough info. You actually do, but you may not realize it. Here's the piece of info that you're not going to be given should you ever have to solve such a problem again. The piece of info that is not going to be given to you, that I'm giving to you right now in hopes that you remember, is that this angle right here is going to be 45 degrees. You see, the pitcher's mound lies on one of the diagonals of the square. The pitcher's mound lies on one of the diagonals of the square. And when you draw in a diagonal, you're cutting that 90-degree angle in half. So that would be 45 degrees. So to find the distance here from pitcher's mound to first base, you're simply going to use, look at this triangle, and you're going to make a law of cosines equation. And I would say x squared is equal to 60.5 squared plus 90 squared minus 2 times 60.5 times 90 times the cosine of 45 degrees. X would actually equal the square root of this entire expression. And I'm going to take a moment to do that on my calculator. I'm coming up with 63.72 feet. So you probably don't find it interesting, and I don't know if you're a baseball player or not, but now think about this. When the batter who's here at home plate hits the ball, let's say the batter hits the ball just a little dribbler right back over to the pitcher. So the pitcher picks up the ball, but by the time the ball hits the bat and goes to the pitcher, 1 or 2 seconds are going to elapse. Then the runner got to run 90 feet over here to get to first base. But the pitcher's only 63 feet away, 64 feet away to start with. So a lot of times what will happen is if the ball goes in this path right here, maybe the ball goes right to here, the first baseman will actually run over and get the ball. The pitcher will run over and cover first base. And then the first baseman will toss the ball to the pitcher on first base. And the question always, well, how is it that the pitcher is able to get over there to catch that ball before the base runner could get there? It's because the base runner has so much farther to run than the pitcher would have to run. That's 2/3 of the distance. Yeah, I'm sure that you're enthralled with that. But anyway, I thought I'd make that point to you. Let's do one more problem. Can you handle just one more problem? All right, maybe 2 more problems. I'm sorry. We'll do one more. Now, maybe, I'll tell you what. I'm going to do 2 more, but you don't have to watch them both. You just have to watch the second one. Anyway, let's go. Let's suppose this is, this right here is, let's say, I don't know, this dot represents Deerfield, Ohio. You know where Deerfield is? The thriving metropolis of Deerfield. That's due west from Canfield. Let's say this is Canfield. And it's from Canfield to Deerfield, it's due west down Route 224. And it's 15 miles from Canfield to Deerfield. Now, over here is Ravenna. I'm sure you've all had reason to go to Ravenna. And Ravenna is 27 miles from Canfield. Right? And Ravenna is in a direction from Canfield, in a direction from Canfield of 140 degrees. Now, flashing back to what we learned about vectors, remember that your direction is always relative to the positive x-axis. So this direction would be 140 degrees off the positive x-axis, which means that this angle right here has to be 40 degrees. And my question is going to be, how far is it from Deerfield to Ravenna? So we know the distance from Canfield to Deerfield. We know the direction is, direction from Canfield to Deerfield would actually be 180 degrees, but we're just saying due west. And then the direction from Canfield to Ravenna is 140 degrees, and it's 27 miles away. So when you look at this situation, I'm hoping you see it as a law of cosines problem. And you would say x squared is equal to 15 squared plus 27 squared minus 2 times 15 times 27 times the cosine of 40 degrees. And x would actually equal the square root of that whole expression. It's time to go to your calculator and get the answer. You think you could listen for one more problem? Let me give you one more problem here. Let's suppose that, this is the shoreline. All right, this is the shore over here. And this is the ocean out here. All right, and this is the port right here. And there's 2 ships. And the 2 ships, they leave port at 8 in the morning. So the 2 ships, they leave port at 8 a.m. 2 ships. They leave port at 8 a.m. Now, one ship travels in a direction of 70 degrees. So let's just kind of put our x-axis here. Now, one ship travels in a direction of 70 degrees. So that would be this way, like this. All right, that's ship number 1 out there. The direction is 70 degrees. So this is ship number 1. All right. All right. And this is 70 degrees right here, this angle. So ship number 2 travels in a direction of 300 degrees. Now, 300 degrees, if you rotate around 300 degrees, then you're going to have, ship's going to be going in this direction. But if this rotation here is 300 degrees, then this angle right here has to be 60 degrees. This angle right here has to be 60 degrees. All right. And let's suppose that this ship here is traveling at a speed, ship number 1 is traveling at a speed of, say, 25 miles per hour. And ship number 2, that's this ship here, number 1, number 2, is traveling at a speed of 20 miles per hour. Now, here's the question. Question is, how far apart are the ships from each other? How far apart are the ships at noon, let's say? All right, at noon. That's the question. So from 8 a.m. to noon would be 4 hours. And ship number 1 was traveling for 4 hours at 25 miles per hour. That's 100 miles. So this would be 100. And ship number 2 was traveling for 4 hours at 20 miles per hour. So that would be 80 miles. And the question is, how far apart are the ships? So that would be this here. Once again, I'm hopeful that you see this as a law of cosines problem. And this entire angle here that you're going to put into your law of cosines relationship would be 130 degrees. And I think if there's anything tricky about the problem, it's that. So when I set this up, here's what I'm going to have. I'm going to call this x, and I'm going to say x squared equals 100 squared plus 80 squared minus 2 times 100 times 80 times the cosine of that 130 degree angle. And then x is actually going to equal the square root of that whole expression. And you just go to your calculator and get the answer. Now, I know it's been an eternity since I started talking, and I apologize for that. But just a very quick review of everything that I spoke to you about. We started with a quick review of law of sines and the law of cosines. Those are the two things you just really need to know, folks. You really need to know how to apply those. Always use law of sines if you can over law of cosines. Law of sines is just more efficient. Then we started talking about finding the area of a triangle, and we said there's different ways to do that. This is your basic formula right here. And that basic formula is what you're going to use really all the time, except different types of given information would warrant using different versions of that. So when you get to a right triangle, remember that the two legs are the same thing as the base and the height. You might have to use some things you know about right triangles in order to find either the base or the height before you can plug into your formula. In this one, we use Pythagorean theorem to find one of the legs. In this problem here, we started going to using a sine relationship to find the height, and we developed this formula right here. So this formula right here is the one you're probably going to use the most. Just remember that. So if you don't know this, you got to know this. Make sure you learn this right here. If you just have three sides for a problem like this or a problem like this, you're probably better off using Heron's formula. The mistake that's most often made by students when they're using Heron's formula is when they find the semi-perimeter, they forget to take half. So don't forget to divide by 2 when you're finding the semi-perimeter. A parallelogram is the formula for a parallelogram. Base times height. Common mistake is to try to take half when you do that. So don't do that. Remember, if you have this triangle sitting in a circle like this, it's an isosceles triangle. Remember that if you're doing a baseball field problem, or it could be softball, or it could be kickball, or something similar, that this angle right here is 45 degrees. This angle right here between the baseline and the diagonal is 45 degrees. Most of the time, the problem will not tell you that, so you need to remember that. This was just sort of a distance problem. By the way, this problem right here, actually the baseball problem too, if you've ever heard of the expression triangulation or triangulating, that's what we're doing when we're solving these problems. We're triangulating, which just means that you're using your geometry and trigonometry knowledge to find the distance between 2 points without actually measuring the distance between 2 points. And then this last problem here was another triangulation problem, just finding the distance between 2 ships without actually measuring it. So I hope that this has been helpful to you. If it wasn't, I'd appreciate you telling me why, and if it was, I'd appreciate you telling me why. And I'm open to suggestions. So until we meet again, you guys stay safe. Thanks for listening. Bye.